Hello everyone. In this lecture we will discuss energy in magnetic field. So here we know that induced EMF this is equal to minus L di over dt. So here L is the self inductance and I is the current here. So intrinsically this L, that is self inductance, is a positive quantity, but here this negative sign shows that the induced EMF oppose the current. So here induced EMF oppose the change in current, so this is known as back EMF. So here in the present this topic we are interested to find the work done against back EMF. So here in this lecture we are interested to find the work done against back EMF. So here this back EMF, this is a fixed amount and recoverable when the current is switched off. So here this work done against back EMF is the energy stored in the magnetic field. So I will repeat this point again. So here, as we discussed, this induced EMF oppose the change in current. So this EMF is known as back EMF. So here this back EMF is fixed in amount and recoverable when we switch off the current. So here this work done against back EMF is nothing. This is the energy stored in the magnetic field. So here for this work done per unit time is equal to induced EMF into I. So when we substitute the value of induced EMF in this equation, then we can write minus L di over dt, and here this is I. So here this is equal to Li di over dt. Okay, then or this question we can write like this, that is dw is equals to Li di. So when we integrate this limit from 0 to I, that is here we start with 0 and end with the total current I, then we can write Li 2 over 2 limit vary from 0 to I, and this is equals to 1 over 2 Li square, and here on the left side we have this W. So here work done is in terms of L, that is self-inductance, and the current. Then we will discuss work done in terms of volume current density. Volume current density. Now here we know that flux phi is equal to B dot dA with the surface integral, or this B we can write curl of vector potential. So here this is dA, again we have a surface integral. Then we can write these questions like this, that is A into dI. So here we apply the Stokes theorem to convert surface integral into line integral. Further, this phi, we know phi is equals to Li. So when we substitute this value phi in this question, suppose this question is this is a first question, then we can write Li equals to A dot di. Okay, now substitute this question, this Li value in this question. Suppose this question is 1 and this question is 2. So here we will substitute the value of Li in the first question. Then we can write W is equals to 1 over 2 I, and here this is A di. Okay, or we can write 1 by 2, this is A into I, or in place of a di we can, in terms of length we can write dl, or in terms of volume current density we can replace I with J and dl with dV. So we can write 1 by 2, and here we have A dot J, and this is a dV. So this is the work done in terms of volume current density, and suppose this is question number 3. Okay, so this is the work done in terms of volume current density, that is J, and dV is the volume integral. Then in continuation of this we will discuss W in terms of magnetic field. So here we will use Ampere's law. So according to Ampere's law, del cross B is equals to mu naught J. So here curl of magnetic field is equals to mu naught J, or J is equal to 1 over mu naught del cross B. So now here we will substitute the value of current density in question 3rd, in the last question. So we can write W equals to 1 by 2, and here we can write A, and J is equals to 1 over mu naught del cross B with dV. So to solve or we can write 1 over 2 mu naught, this is a dot del cross B, this is a dV. So to solve this equation we will use vector identity. So according to one of our vector identities, we have this vector identity, that is divergence of A cross B is equal to B dot del cross A minus A del cross B, or as per our requirement we can write A, that is this factor, that is A dot del cross B is equal to B dot del cross A minus del A cross B. Further, this del cross A is equals to magnetic field, so we can write B dot B minus del, that is divergence of A cross B, or further we can write B square minus divergence of A cross B. So now we will substitute the value of A dot del cross B in this equation. Suppose this question number is 4th. So we can write this W is equals to 1 over 2 mu naught, and here this is a B square dV minus del dot A cross B dV, or we can write this is equals to 1 over 2 mu naught square, and here we have a closed integral also. This is a B square dV minus here 1 over 2 mu naught, and this is a cross B, and here this is a dA. So here we apply the divergence theorem to convert volume integral into a surface integral. Then here if we integrate over all the space, then the surface integral, that is this second term of this question, is equals to 0, and we can write that this work done is equals to 1 over 2 mu naught B square dV for all space. So this is the work done against back EMF. So here we can say that finally we can say that the energy is stored in the magnetic field energy is stored in the magnetic field in the amount b square over 2 mu naught per unit volume. Okay, so here in this lecture we discussed work done against back EMF in terms of inductance, then in terms of volume current density, and then in terms of magnetic field. Okay, thank you.